In this video, we will look at complements, subsets, and discuss Venn diagrams. Of course, we see Venn diagrams or those graphs or those images that display overlapping circles to show that two sets may have something in common. We may also see that those two circles are separated or disjointed, meaning that there is nothing in common. So let's look at the definition of the complement, but first let's talk about the universal set. The universal set is the set of all elements that are being considered. But the complement of a set, denoted by A prime, notice the A with an apostrophe, we read that as A prime or A complement, is the set of all elements of the universal set that are not elements of A. So let's think about that for a moment. In order to determine the complement of a set, well, first and foremost, you need to know the elements that are in A as well as the elements that are in U, the universal set. So if you know all elements in the universal set and you can define a set of elements from the universal, then every other element that is not in A would be in the complement of A. So when you think about complements, think about flipping a coin, right? There's only two outcomes, heads or tails. If you flip heads, the complement is tails, and thus the complement of tails is heads. If you roll a die and it lands on a 3, well, the complement of 3 is everything else but 3. That is 1, 2, 4, 5, and 6. So to determine the complement of a set, we must know all elements of one set A as well as all elements of the universal set. So we'll look at some examples here. We're going to let our universal set be defined by the following counting numbers from 1 through 10. We'll define our set S to be the elements 2, 4, 6, and 7. So our first example, if S contains those 4 elements, then what is S complement? Well, it's going to be all of those numbers that aren't in S. Lastly here, our set T is the set of X's such that X is less than 10 and X belongs to the odd counting numbers. Give you a moment there, first and foremost, right? Do part A, and then to get to part B, well, in order to define the complement of T, let's first write out all of the elements. Let's use the roster method for our set T. Give you a moment here to pause the video, and we will pick up with these two examples. If our set S contains 2, 4, 6, and 7, then S complement will be every other number in the universal set that is not 2, 4, 6, or 7. That is 1, 3, 5, 8, 9, and 10. All of the numbers in the universal set that are not in S defines S complement. Now, what about part B? Well, first off, in order to find the complement of T, let's define T itself. They give us the set builder notation. Let's use the roster method. All odd counting numbers, so natural numbers less than 10 that are also odd. That's 9, 7, 5, 3, and 1. So you see there that the set T consists of the odd numbers 1, 3, 5, 7, and 9. So what numbers are in the universal set that are not 1, 3, 5, 7, and 9? Well, it's every other number, 2, 4, 6, 8, and 10. So in order to find the complement of a set, we first need to determine, well, what is the set that we're trying to find the complement of? And also, what is the universal set? When you think universe, think big. So the universal set defined using capital U, that's the large set that we are considering. And then from there, we can pluck smaller sets called subsets out of the universal set. We'll look at two more examples here of finding the complements of M and P. Now, to find M complement, we need to know the universal set as well as M. In order to find P complement, we need to know the universal set as well as P. So let's work these together. Let's look at the first example. U contains only the numbers 0, 2, 3, 4, 6, 7, and 17. So I'll go ahead and write that down. 0, 2, 3, 4. As well as 0, 2, 3, 4, 6, 7, and 17. So within the universal set, we have now defined set M to be 0, 4, 6, and 17. Now, in order to find the complement of M, let's go ahead and go to the full screen. Think about this. Now, you don't have to do this each time, but this is sort of the evaluation mentally that we want to have take place. M complement, the complement of M, every number in U that is not in M. So think about this. M contains 0. So M complement cannot contain 0. So in theory, right, we're just going to go through here and mark out 0, 4, 6, and 17, and everything that remains is in M complement. Let's try that out. There goes 0. There goes 4, as well as 6, as well as 17. So what's left over? 2, 3, 7. M complement is the set of elements 2, 3, and 7. We'll go back to the second example here, and as my screen is blacked out, we'll pull that back up there. P is the set of numbers such that x is less than 7, and x belongs to the even natural numbers. So let's take a moment there to define what P is before we find P complement. So P must be less than 7, and P must be an even natural number. So what are the numbers less than 7? Well, 6. 6 is less than 7, and 6 is an even natural number. Well, going below that, we have 4, an even natural number that's less than 7. And then we go to 3. Well, 3 is not even, so we're going to skip it. Then we go to 2. The last element to consider is 0, and although 0 is an even number, it's not natural, right? It is not one of the counting numbers that we described in our last video. 0 is a whole number. 0 is an integer. 0 is a rational number. 0 is a real number. 0 is not a counting number. So this is our set for P. P contains the elements 6, 4, and 2. Now, it is common and it's preferred that once we list out our elements, 6, 4, 2, that we go ahead and arrange them in the correct order of ascending order, smallest followed by largest. So I'm simply just going to switch around the 6 and the 2. There's nothing wrong about leaving it in an incorrect order, so to speak, but there's always things that we prefer. And in this case here, we prefer our numbers to be from smallest to largest. So if P contains only 2, 4, and 6, then P prime or P complement is going to contain everything else from U that isn't 2, 4, or 6. So let's list it. Starting with 0, we'll skip 2 and we'll include 3. We will skip 4 and 6, but include 7. And then lastly, we'll include 17. So notice here, right, that the universal set has 7 elements. P has 3 elements. P complement has 4 elements. So of course, if you think about it, adding up the cardinality of any set and its complement, well, that cardinality, when you add them two together, should be the same as the cardinality of U, because that is the set of elements that are being considered for any set and its complement. I'll go to the full screen so that we can see that. That if P is 2, 4, and 6, then P complement is 0, 3, 7, and 17. And if you don't believe me there, we'll go ahead and go to the next slide, right, and kind of see that listed there for us, right? M is 0, 4, 6, and 17. Therefore, M complement is 2, 3, and 7. P is 2, 4, and 6. Therefore, P prime or P complement 0, 3, 7, and 17. Well, here's something interesting for us to consider is that if a set contains a complement, then what's the complement of the universal set? Remember that the universal set consists of all elements that are being considered. So what's the complement of everything? Ooh, you might guess it. The complement of everything is nothing. And the set that represents nothing is the empty set. So here the complement of the universal set is the empty set, and therefore the complement of the empty set is the universal set. So that's what we're seeing here. The first equality says that U complement. That's saying that the complement of the universal set is the empty set, and the complement of the empty set is the universal set. That leads us into subsets. Note that we just discussed pulling sets from the universal set. So the universal set was the large set, but then we had smaller sets called subsets. So consider the set of letters in the alphabet, right? A, B, C, D, E, F, G, all the way to Z. Well, we can pluck out consonants, those 21 consonants, or those 5 vowels. Well, if you just define the set of vowels, that set comes from or derives from the set of letters of the English alphabet. Every element of the set of vowels is an element of the set of letters in the English alphabet. The set of vowels is said to be a subset of the set of letters in the alphabet, and we will often find it useful to examine subsets of a given set. Sort of like in statistics, we use a population, and from the population, we grab a sample. So just as in statistics, we study samples from a population, here we will study subsets from a given set. So using mathematical notation, we now can describe a subset from any set. For example, set A is a subset of set B, denoted as follows. We see there what looks like a round U shape that's sitting sideways with a line underneath, kind of like less than or equal to, but notice there that we don't use the hard corner. We have a roundedness to it. So here A is a subset of B if and only if every element of A is also an element of B. In other words, we should be able to find A living within our set B. So A is a subset of B if every element in A is also an element of B. The fundamental subset relationships. Here's something interesting, is that A is a subset of A. In other words, any set is a subset of itself, because by definition, every element within a set is an element within itself. So any set is a subset of itself. And then lastly here, notice the notation, it says that the empty set is a subset of A. In other words, for any set, however you want to define your set, the empty set is always considered a subset, because we can consider that, well, we can always find nothing within something. And that's our idea there, that the empty set, no matter what or how you define your set, the empty set will always be a subset of that set. Do note that in order to show that a set is not a subset of a set, then think back to the last video where we slashed through our notation that showed that an element belonged to a set. In this case here, right, we read the following mathematical notation: A is not a subset of B, by using the subset notation and placing a slash through it. To show that A is not a subset of B, it is necessary to find at least one element of A that is not in an element of B. So we just need to find a counterexample. Find one scenario, one instance, where an element in A is not in B, and you have shown that A is not a subset of B. Let's go to an example. Determine whether each statement is true or false. For the 4 examples listed here, we want to go down one by one and determine if the set on the left is actually a subset of the set on the right. That is, if you look at part A, it's asking, is 5, 10, 15, and 20 a subset of 0, 5, 10, 15, 20, 25, and 30? And as you see, yes, it is. That is true, because 5, 10, 15, and 20 can be found on the right. Therefore, part A, we have a subset that is true. Now, what about part B? Part B is interesting, right? Part B asks, is W a subset of N? Remember what these represent. W represents whole numbers, N represents natural numbers. Here, this is false. W is not a subset of N. And I want to go to the full screen here. This is what's given to us. This is false. To make this a true statement, we simply place the slash mark through our subset notation. My question to you then would be, what would happen if we spun these two sets around? That is the question here. Is the set of natural numbers a subset of the whole numbers? This is true. Think about this. The natural numbers, 1, 2, 3, 4, 5, and so on, are found within the whole numbers, 0, 1, 2, 3, 4, 5, and so on. So this is true, whereas this is false. Note that the whole numbers contain 0. 0 is not in the set of natural numbers. So that's why we have found a counterexample of a number being in here that is not in here. But if you switch them, you get something that's true. Every number that's a natural number is also a whole number. Let's go back to that page with our examples here. Look at part C, asking the question, is the set with elements 2, 4, and 6 a subset of the set with elements 2, 4, and 6? Well, let's take a look at that, right? They're the exact same. They're the exact same. Go back to the video, within the video, and see that every set is a subset of itself. So C, we have a true statement. And then lastly, part D, is the empty set a subset of the set 1, 2, 3? And that answer again, right, is yes, this is a true statement. The empty set is a subset for all sets. So here on the slide, we will pull up our description of each, right? For part A, every element of the first set is an element of the second set. For part B, right, we have a false statement because 0 is a whole number, but 0 is not a natural number. That's our false. C is true. Every set is a subset of itself. You see there that every number or element on the left is also contained in the right. And then lastly, we get a true statement because the empty set is a subset for every set, right? Even for itself, the empty set is a subset for the empty set. So you'll always see a true statement if it looks like part D. The empty set is always a subset for any set we define. So we can have a few more examples at our disposal here, determine whether each statement is true or false. Our first example is asking, is 135 a subset of 159? That answer is no. This is a false statement. 135 is not a subset. You see there that 3 is contained on the left and it is not contained on the right. That is our counter example. 3 does not belong to 159. So I'm going to write this up here. I'm writing out that 135 is not a subset. So I'm placing in the slash, and then I'm going to write out the 159 on the right. So just to think about this, right? What's on the PowerPoint is false. But by putting the slash now through the subset notation, this is now a true statement. And the reason is why, right? What is that one counter example? Why is this the case? And it's because of 3, right? 1 can be found over here. 5 can be found over here, but 3 cannot. So let's go back to that notation of is an element, right? 3 is not an element. Three does not belong to our set 159. This here alone, right? This is our counterexample. 3 does not belong to 159. Therefore, this set is not a subset for this set. Let's go back to our examples here. Our next example says, well, is -6, 0, and 11 a subset of the integers? Well, -6 is an integer, 0 is an integer, 11 is an integer. So that's true. The set of 3 elements is a subset of the integers. Last one here, the set of counting numbers is a subset of the set of natural numbers. Is that true or false? Yeah, we want to review our previous video that says that, well, the counting numbers and natural numbers are the same thing, right? We can refer to natural numbers as counting numbers and vice versa. So in this instance here, we have a true statement. The set of counting numbers is the same set as the set of natural numbers, and every set is a subset of itself. Some applications require that we find all of the subsets of a given set, just to know what we're working with. One way to find all the subsets is to use the method of making a list, right? Let's organize all the possible subsets for one particular set. First, we want to list the empty set because, as we know, the empty set is a subset for any set we want to create. Next, list all the sets that have exactly one element, list all the sets that have two elements, followed by three elements, and so on, however far you need to go. We'll take a look at an example. List all the subsets for the following set, A, B, C, D, and E. So notice here that we have 5 elements within our set. The first thing we want to do, list the elements with 0 sets. That's the empty set, so we have it listed. We then proceed with listing all sets that have exactly one element. So the set of A, the set of B, the set of C, etc. Subsets with 2 elements. Well, notice here we're just kind of going in order, right? Start with AB, then AC, AD, AE. So we've exhausted all possibilities where A is in a set with 2 elements. Then we go B, C, B, D, B, E. Notice we don't have to write BA because BA is the same as AB. Then we go to C, D, C, E. Then we go to D, E. And those are all possible subsets that contain 2 elements. Then we move on to 3 and 4 and 5 and so forth. Again, with this example here, the process is illustrated, and we're gathering the idea of how to find all subsets for one particular set. We'll take a look at an example. We started large, and that's a good thing, but let's just maybe work our way back. A set contains letters, they contain numbers, they contain words, descriptions, and so forth. So in the context of mathematical sets, let's work with numbers, right? Just choosing any 3 numbers we want. And at home, I encourage you to choose 3 different numbers that I work with. But just throwing numbers out, I'll say 13, 18, and 27. There's no rhyme or reason why I chose these 3 numbers. They were just the first 3 that came to mind that weren't 1, 2, and 3. So we have 13, 18, and 27. Let's list all subsets for this one particular set, starting with 0 elements. Well, that's our empty set. Followed by all subsets with 1 element. So we're just going to now list 13 as its own set, 18, and 27. We have 3 subsets that contain exactly 1 element. Then we go to 2 subsets. 2 elements within a subset. And where do we start, right? There's no real right way to start. So just ideally, right, reading left to right, we'll start with 13 and 18. Next, 13 and 27. Those are my only possibilities of having 2 elements with 13. So then we'll go to that last one there, as you see, 18 and 27. You can think of more possibilities, list them, but here we have our only options. And then lastly, right, 0 elements, 1 element, 2 elements, and then lastly, right, the 1 subset that contains all 3 elements is the set itself. So as we can count here, how many subsets will we have when our set contains 3 elements? And this will be, if you choose your 3 numbers at home, you're going to have the same number of subsets, right? That's not going to change. The way they look changes based on the numbers we've chosen, but how many we have, that's going to be the same no matter what your 3 elements are. 1, 2, 3, 4, 5, 6, 7, 8. You end up with 8 subsets for your set of 3 elements. And maybe we want to start thinking about that. Why was it the number 8? Why did that appear? Where does 8 come from? We're going to see momentarily a nice little formula that we will be able to use to predict every single time how many subsets does a particular set contain. Keep in mind, you choose any 3 other numbers or even any 3 letters. If you choose 3 letters in a set, you're going to have only 8 distinct subsets. Doesn't matter what your 3 elements are. So because that pattern is always going to occur, think about that mathematically. When you find a pattern, you have some kind of model or formula that represents that pattern. And we're going to see that momentarily in the video. The English logician John Venn developed diagrams, which we now refer to as Venn diagrams, that can be used to illustrate sets and relationships between sets. In a Venn diagram, the universal set is represented by a rectangular region, and the subsets of the universal set are generally represented by oval or circular regions drawn inside the rectangle. The Venn diagram below shows a universal set and one of its subset labeled as set A. The size of the circle is not a concern. It's merely just an image for us to work with to determine what falls in a set, out of a set, what's in common, not in common, etc. The region outside of the circle, but inside of the rectangle, represents the complement of A. So as we started at the beginning of the video, your universal set is whatever number or sets of numbers are of interest to us. And then from there, we can define sets within the universal set. Anything that we do not define within a set is the complement of that set. So again, if we need to refresh earlier in the video for any set and its complement. An exercise that we're going to now revisit from earlier in the video is to draw a Venn diagram for each of our examples that we use. That is, for our universal set 0, 2, 3, 4, 6, 7, and 17, we defined M to be 0, 4, 6, 17, and therefore we said that M prime or M complement was 2, 3, 7, right? And then P was those even natural numbers less than 7. So we had 6, 4, and 2. Therefore, P prime or P complement was 0, 3, 7, and 17. Let's use that information to now create a Venn diagram. Pause the video to try this out for the first example, M, and then we will work that out together after you pause the video. We will look at the first example involving M and M complement, and I will now go to the full screen. As you see here, we've listed the set M and its complement, M prime. And so now we're going to create the Venn diagram. And as it suggests, right, we're going to use a rectangular box to denote the universal set. All this means is at the end of the day, all of the numbers found in U should be somewhere in this box. Now we'll go to M, right? That's the set of interest. We will use a circle to denote the set M that lives inside of U. So here, our box is the universal set. Our circle will be defined as the set M. And as we note, M contains 0, 4, 6, and 17. So we'll place them directly in our circle. So far, so good. Now, what about the remaining numbers? Because as you see, right, M contains 0, 4, 6, and 17. Likewise, 0, 4, 6, and 17 is also inside the box. And that's what U is. And we can see 0, 4, 6, and 17 in U as well. But what about everything else in U? What about the 2? What about the 3? What about the 7? Well, those are the numbers here. So if this is the complement of M, if M is the circle, then M complement is everything else inside of the rectangle, meaning that M complement 2, 3, and 7, those 3 numbers are just floating somewhere inside the rectangle, but outside of the circle. So we'll place them on the exterior, 2, 3, and 7. It does not matter where you place them as long as you don't place them in the circle. However, you do place them in the rectangle. Now take a look. If the rectangle represents the universal set, every number in the universal set is now inside the rectangle. Every number defining M is inside the circle. Every number that defines M complement is outside of the circle, but inside of our rectangle. We'll now go to our second example. Take a look at P and go ahead and remind yourself, how did you define P? How did you define P prime? Do a little bit of erasing up here. Our universal set is still the same. So I'm going to use the same rectangular box for U. P, however, It's numbers less than 7 and even natural numbers. So numbers less than 7, that is 6, 4, and 2. So the complement of P, everything else, 0. Let's see here. We have 3, 7, and 17. So let's try this again, right? Draw a circle, label the circle as P, and therefore everything else is going to be that P prime. I'll go to the full screen again. Once more for P, 2, 4, 6, we're going to place them in the circle. And all the other numbers, 0, 3, 7, and 17, will be in the box outside of the circle. And that's it. In order to create a Venn diagram, we have a rectangular box and we have a circular figure in the middle. And there you go. The next discussion will be regarding proper subsets. A proper subset, denoted as above, notice it looks similar to the subset notation, but we do not place the horizontal line below. We have here that A is a proper subset of B if every element of A is an element of B and A cannot equal B. Well, that's interesting because we've already looked at 2 examples where we list every single subset that we can possibly have. And we got down to the end and found that the set itself is a subset of the set. But it's not a proper subset. Proper subsets are sets, but the 2 sets can't be equal. So all we have to do here to find proper subsets is to simply erase that bottom set. What do we mean? Let's go back to that example, right? Let me pull this back up. We use those 3 numbers from before, but let's just go ahead and switch it up to say A, B, and C, right? Here I have a set containing 3 elements, and as we mentioned earlier in the video, that I know I'm going to have 8 distinct subsets. All right, I'll have 8 subsets, but how many proper subsets will I have? 7. In other words, if I can find all of my subsets, including the set itself, well, if I just simply remove the set from the list of subsets, I will have all of the proper subsets. Let's remind ourselves. The empty set, that's a subset. A is a subset. B is a subset. C is a subset. Going to the sets with 2 elements, AB is a subset. AC is a subset. BC is a subset. So these are each of our 3 subsets containing only 2 elements. The last one here is the set itself, ABC. Right? These are our 8 subsets. But which are the proper subsets? Each of the subsets that isn't the set itself are proper subsets. You just subtract out the one that contains all the elements. But keep in mind that all of them are subsets. So subsets, all the elements from the original set are in that set itself. Proper subsets, you just simply eliminate the one subset that is equal to the set that's in question. Some examples to consider: let the following set R represent the planets Mars and Venus, and let the set S represent the planets Mars, Venus, and Mercury. Now notice here that the set R contains 2 elements that can be found within S. So we have a subset, and more specifically, because R and S are not the same sets, this means that R, not only is it a subset, but it's a proper subset, simply because it's not the set S itself. Second example, let T equal the continents of Europe and Europe and Africa, and let V represent the continents Africa and Europe. Well, this is interesting, Because we listed the same two continents, right? But we just placed them in a different order. No biggie there, it's the same two elements. Now keep in mind, when the two sets are exactly the same, we have a subset. But we do not have a proper subset. When the two sets are equal, they are subsets, but they are not proper subsets. For each of the following examples, determine whether the first set is a proper subset of the second. Now again, going back to some examples we've seen thus far, we have here the set of vowels in our English alphabet, A, E, I, O, U, followed by the set E, I, O, U, A. Same elements, right? Same letters that we're looking at. They're just organized or ordered differently. The sets are the same. They're equal. So for part A, although they are subsets of one another, they're not proper subsets. But what about part B? It says N and I. Now, N is the set of natural numbers. I is the set of integers. Is N a proper subset of I? Yes. The reason for this, right, is every natural number, 1, 2, 3, 4, and so on, can be found within the set of integers. Moreover, these two sets are not equal. Therefore, N is a proper subset of I, and we would use the notation N is a proper subset of I, just meaning that everything over here can be found in here. Additionally, these two sets are not equal. So in some applications, we need to determine the number of subsets without actually making a list of all the subsets themselves. We know that the empty set has 0 elements, and the only subset of the empty set is the empty set. A set with 1 element has 2 subsets, namely itself and the empty set. It is easy to show that a set with 2 elements has 4 subsets, and a set with 3 elements has 8 subsets. In example 4, we found that a set with 4 elements has 16 subsets. We can show that, right? If we list out 4 elements in a set, starting with the empty set, starting with the sets containing only 1 element, followed by 2, followed by 3, and followed by 4, we will be able to count out that there are exactly 16 subsets. And so the following page here gives a nice explanation of the number of subsets. Here, if we have, say, for example, 4 or 5 or 6, what does the pattern suggest for the number of subsets? Again, it's all about establishing a pattern here. 1 followed by 2, followed by 4, followed by 8. What are those numbers doing? As we increase the number of elements by 1, what do the number of subsets do? Well, they're doubling, right? 1 doubles to 2, 2 doubles to 4, 4 doubles to 8, 8 doubles to 16. If we double 16, what do we get? We get 32. If we double 32, we get 64. So what's the pattern suggesting? It suggests that we multiply by 2. So what does that look like as a pattern? What would the notation tell us? Well, since we're multiplying by 2, we're just increasing our power of 2. That is, here's the big part here, right? We're introducing now a formula, so to speak, right, to determine the number of subsets. A set with n elements, let n represent the number of elements. So if it's 4, then you will have 2 to the 4th power subsets. 2 to the 4th power, or 2 times 2 times 2 times 2, as we see, is 16. We've already shown that if we have 3 elements, we know that we're going to get 8 subsets. Well, note here that 2 to the 3rd power, 2 times 2 times 2, is equal to 8. A set with n elements will have 2 to the power of n subsets. And that would then lead us to the proper subsets. As we declared before in the video, in order to find the number of proper subsets, we simply eliminate just the one. By eliminate, I mean subtract one. I subtract or take away that one set that is equal to the original set. Remember that a proper subset, the two sets cannot be equal to one another. So take away the one subset that's actually the set itself. Therefore, a set with n elements has 2 to the n power minus 1 proper subsets. So first plug n into the formula, 2 to the n power, and whatever number you get, simply subtract 1. That's your number of proper subsets. An application that we can see for using subsets is fixing or detailing a car to our liking. That is, a company makes a car with 11 upgrade options. Think of this as getting Wi-Fi in the car, having a phone in the car, having better signal, having Bluetooth capabilities, having Sirius XM radio, whatever it is, whatever upgrades you can have. Maybe going from electric windows, used to have the roll window, but you would have to upgrade, pay more to get the electric windows. So you have 11 upgrade options. Now keep in mind that these options are independent of the other, so you can have 0 upgrades, you could have 3 upgrades, you could have all 11 upgrades. It doesn't matter. How many different versions of this car can the company produce? Well, as we mentioned before, right, it's a matter of listing the subsets, right? If you think about all 11 options listed out in the roster method, those are your 11 choices. You can plug in any of those you want. Do you want just 3 options? Do you want 7 options? But which of those 3 options do you want? Maybe it's the window, seating, and radio. Maybe it's the radio, the window tint, and the extra space. There's so many different ways you can just choose 3 out of 11. So what are all the different possibilities? Well, you imagine taking 11 elements and listing all the possible subsets. As we said before, n elements means that we have 2 to the n power subsets. So essentially here, to find the number of upgrade possibilities, the number of different versions, we're just simply going to take 2 and raise it to the 11th power. That is, 2 to the 11th power equals 2048. Thus, the company can produce 2048 different versions of this car based on the upgrades that it has. An exercise similar to what we just saw sort of begs the question, well, if we don't know the number of upgrade options, but we know the total number of versions, well, can we work our way back? In other words, instead of plugging in to determine the number of versions, what if we know the number of versions and therefore we need to determine n? So part B for this exercise is going to give us sort of an idea of how to go about that. It says, what is the minimum number of upgrade options the company must provide if it wishes to offer at least 8,000 different versions of the car? So it doesn't say here we have 8,000 upgrade options. Here they're telling us that we have 8,000 different subsets. So how many elements do we need in order to have 8,000 different versions or subsets for this particular car? And from our previous example, we already saw that 2 to the 11th power is 2048. Well, as we know here, if we increase our number of elements by 1, we double the outcome. So by going from 11 to 12 options, we go from 2048 to double that, 4096. Again, by increasing the number of options by 1, now we have 13 options, 13 upgrade options. 2 to the 13th power is 8,192. There we go. We have now meeting the criteria, at least 8,000 different versions. We see here, if we have 13 upgrade options, then we have at least 8,000 different options. Thus, the company must provide a minimum of 13 upgrade options if it wishes to offer at least 8,000 different versions of the car. Stripping some examples here from our text exercises, I look at number 62. It says here a set has 1,024 subsets. How many different elements are in the set? So again, similar to the previous example, in this case, we're trying to determine what is that exponent? What are the number of elements to give us that outcome of 1,024? So here we're going to play with our formula 2 to the n power. By plugging in some exponents, we're going to try to determine what is our value for n, therefore how many elements. Well, using that last example, right, kind of playing off of that, 2 to the 11th power, grabbing my calculator, right, we saw that that was, what, 2048. Right, 2 to the 11th power is 2048. We want 1024, and it's just convenient for us that half of 2048 is 1024. So therefore, by the pattern, if we decreased our number of options by 1, then we're halving our total options. In other words, if the exponent 11 gives us 2048, notice here that the exponent 10, in other words, 2 to the power of 10, is 1024. So for part A, how many elements are in the set? 10. 10 elements will give you 1024 subsets. Part B says that a set has 255 proper subsets. Now notice the difference in terminology, proper subsets versus subsets. How many elements are in the set? Well, 2 to the n power only applies to subsets. When we say proper subsets, it's 2 to the n power minus 1. And that's what's happened here. That's why we have an odd number, 255, right? If you double numbers, if you double integers, you're always going to have an even number. Of course, that pesky 1 at the end where we initially start, but everything else after that, right? 2, 4, 8, 16, 32, 64, and so forth. When we double, we have that even outcome. Now, notice here it's odd. That's because we had to subtract 1. Well, we subtracted 1 to get 255, which means 256 is the number of subsets. What is the exponent that takes us to 256, right? 2 to the power of what gives us 256? Well, we'll go to our calculator and I'll just start hitting numbers, right? 2 to the power of 8, there it is. 2 to the 8th power is 256. So what that tells us is if you have 8 elements, you will have 256 subsets. Therefore, subtracting 1, you will have 255 proper subsets. For part B, 8 elements will give us 255 proper subsets. And lastly, part C, is it possible for a set to have an odd number of subsets? Well, like I explained it in the above example, but let's think about that. If you double a number, it's even, 2, 4, 6, 8, 16, and so forth. What was that first number we started with? It's 1. In other words, if you have a set with 0 elements, 2 to the power of 0, keep in mind, right? Our mathematical rule here is if we have a number whose exponent is 0, well, that output is 1. Anytime your exponent is 0, as long as this number isn't 0, right, this is always going to give us a 1. 5 to the 0 power is 1. 1/2 to the 0 power is 1. So here, 2 to the power of 0 equals 1. But what does that mean in the context of subsets? It means that if we have a set containing 0 elements, then we have exactly one subset. What is that set? It's the empty set. The empty set is the only set that contains 0 elements. How many subsets does the empty set have? Just one. Every set is a subset of itself. And the only set here that we're going to have an odd number of subsets is our empty set.